Hello, Calc. We're watching this Monday after class, 11:6, and we're going to use Rolle's theorem in order to develop a new theorem, and that's the real reason we learn Rolle's. So I'll go ahead and develop that if you would write down the development as we go, and I will alert you when we have the development complete. You may not recognize it, so I'll be sure to show you. Draw a function that looks like this. I chose this function to be f of x. Any old function will do. And notice it's continuous and differentiable on the interval between a and b, as long as the portion where we look for continuity is on the closed interval ab, and the differential part is on the open interval AB. And I'm also going to, let me move the B down a little bit. If you would make sure your A and your B are sort of at different heights. Mine didn't turn up as like I wanted it to. How about now if I call that B? Then f of B and f of A. So f of A would be over here, and f of B would be over here. Remember, you go up from A, hit the function, and that's the function at A, or f of A. This is B, go up and hit the function, and that's f of B. Alright, now I'm going to draw a secant between the 2 points. And notice that is a straight line, and the secant has the same value here of A on it and B on it. Let's call the secant g of x. So now g of A will be at the same spot as f of A was. And g of b is at the same spot as f of b. So I'll indicate that they're equal because they intersect at the same point. So I'll also write that over here just to make it abundantly clear and usable in a minute. F of a equals g of a because they intersect, and f of b, right here, f of b equals g of b because they intersect. So if this is g of b, and it's also f of b. This is f of a because it's on f at the point A, and it's on g at the point A. They intersect. Alright, so now I'm going to define another function altogether. It's not f or g, it's h, and it's the difference between the f function and the g function. So if I was going to graph it, I would see if I start here at this point, the difference between the two functions is 0. So that'll be 1 point on my h function. But then I'm going to see that the difference is small but growing. See the difference between the two? This line's getting bigger, so the function will come up like that. Then it'll start to shrink until it hits 0 again. So this is my function h of x. So h of x is the difference between the two. Just going to move that name. Alright. So I'll call it h of x, which is the difference between the upper function f of x and the lower function g of x. Our properties of derivatives, if we want to know the derivative of h of x, we know the derivative of a sum, in this case a difference. Same principle is the difference of the derivatives. So we can take the derivatives across like that and have a valid statement. Alright, let's look at the next part. I want to establish something about h, that's the dysfunction, h at A and h at B. What would you notice about those two? H at A and h at B. We can see because it's the difference of the two, and at this point there is no difference between the two, and there's no difference between the two at this point. So in the difference function h of A and h of B are both equal to 0, so I can say that they are equal to each other and to 0. So make that. So this is a prerequisite. As long as this is continuous on the closed interval AB and differentiable on the open interval AB, which it is, we can use Rolle's theorem. So can you roll out Rolle's theorem for me? So by Rolle's, we can say there is a value C, and that's in the interval AB, such that, what? Can you finish it for me? Remember we learned that if this happens to equal 0, and in Rolle's all we had to say was f of A equals f of B. And this just happened to also be equal to 0. Rolle's does not require that. They just have to be equal to each other. There is a C such that h prime at C equals what? What does Rolle's guarantee? It guarantees that there's a C somewhere. I'll put it right there. So that it has a derivative of 0. And if we go up here, we found the spot right there where the derivative is 0, the tangent being a horizontal line. All right, so now we're going to do some substitution and putting some statements inside of others until I have something more useful. So now I know I've got h prime at C equals 0, and I know from this statement that no matter what function I put in here, whatever I put in this function, like an x, equals this evaluated at x minus this evaluated at x. Well, I'm going to put in a C everywhere there's an x. And again, that's coming from this line. So it's true for any value, so I'm going to choose C. And I also know that h prime of C is 0, so I'm going to place 0 because I've established that by Rolle's. I'm going to put h prime of C equals 0. So now I can rearrange that so that I can say, I'll put it like this, f prime of C equals g prime at C. That's just a rearrangement of the statement above it. And now I'm going to indicate that f prime at C equals g prime at C. So I'm going to just take this part right here for a second and find what g prime of C equals. Going back to my sketch, I see g is a secant line, and it's a straight line. So I know the slope of a straight line because the slope of the straight line is y2 minus y1 over x2 minus x1. So in this, I have my x1 and my y1, my x2 and my y2. So I'm going to fill in those values from the picture. So I'm going to say g at B minus g of A over B minus A. because I know the slope of a straight line is y2 minus y1 over x2 minus x1. So I'm doing that with these 2 points. I'll put it a little more clear. This is b and g of b. We're on the graph G here. And this is A, and its y value is, why do I keep doing F? G. G is this straight line I called G. G of A. All right. A, G of A, B, G of B. So I've got y2 minus y1 over x2 minus x1. And that is the slope. Derivative at this point, C, it's the slope of that graph. And the slope is everywhere the same. So now I'm going to substitute and get what I want. I'm going to substitute f prime of C. Is there anything up here I can substitute for f prime at C? Well, I see right here. I'm sorry, is there anything I can substitute for g prime at C? Well, it's f prime of C. Gave it away. And so I have f prime of C. Is there anything I can substitute for g of B? Very first statements, I have g of B is the same as f of B. So I'm going to replace that. Is there anything I can replace g of A with? G of A is f of A. So I have what I have aimed for. And I have now established what is called the mean value theorem. Even though it's very nice. The mean value theorem is simply that. And now we'll discuss what it actually means. So they're going to look at the nice mean value theorem and discuss its value. Why is that important? So this time I'll just take any function and any a and any b. So now I want to look at where this function hits the graph, so that is my f of a, and where this b hits the graph, and that's my f of b. I'm going to draw a line between those 2 points. All right, and what I've drawn here, if I could find the average rate of change of the function between 2 points A and B, the slope of this line would be it. So let me write that, and I want you to write that as well. First of all, find the average rate of change Find the average rate of change of a function between 2 points A and B. So here's my point A on the function, here's my point B. The average rate of change of that function between the two is found by drawing a secant line between the two points and finding the slope, the change in y over the change in x. So it would be f of b minus f of a over b minus a. All right, we're good with straight lines. And what the mean value theorem has that in the middle, at the end of it. So what this part is saying is there exists somewhere on this function between a and b a value c that has the same slope as this secant line. So would it be here? No. The slope there is to the tangent here. Would it be here? No. So it's going to be right there.